generic the high level picture, and then I will hopefully get into some proofs and the basic ideas of what we do. And I think there's a few things swept under the rug. So if you see something that doesn't make sense, definitely ask a question. There's a good chance it's because it's actually hiding some detail. So I'll go ahead and get started. Yeah, so first of all, this talk is about geodesic optimization for the null cone problem. And we're studying things that must be familiar to you all. We want to study invariance of groups acting on vector spaces. And we are trying to solve them through optimization, in particular by optimizing norms. And there's a nice geometry on these groups where you can just use first and second order optimization methods. And what we do is come up with a pretty general framework which explains the success and failure of previous algorithms for invariant theoretic questions. Okay, so here's an outline. And let's go ahead and get started with the definitions and examples of group actions, but I think these will be pretty familiar from some of the talks before and from Raphael's talk. So group actions, the groups we want to consider are things like GLN, or diagonal matrices, or products of SLNs and things like that, in general reductive groups. And they're going to act on some vector space, which will be finite dimensional. We can think of it as C to the M if we want. I will call it V. And it'll act as G dot V. For example, the conjugation action, where the group acts on the space of matrices by conjugation, or the left-right action, where a product of SLNs acts on tuples of matrices by simultaneously acting on the left and the right. Another interesting one is tensor scaling, where a triple of invertible matrices acts on tensor by acting by the tensor product. And then finally, quivers, where you have a directed graph with some linear maps on the edges and vector spaces as the vertices, and maybe you have the action of one, I guess it's ambiguous in this picture because it's a triangle, but one group element per vertex, and you can see in the picture how it acts on the linear maps on the edges. Yeah, so these are all kinds of things we want to consider. And we want to think about questions about orbits, in particular, like when are two vectors equivalent, or questions like that. And our starting kind of question that we want to answer is, are two vectors in the orbit of the other? We won't be able to answer this kind of question in this talk, but this motivates things. And I'll go kind of quickly through this because I think that this audience doesn't really need a lot of explanation of how this is related to invariant theory, but I'll still go through it. So as we know, if V and W are in the same orbit, then their values agree for every G invariant polynomial. And for reductive algebraic groups, this is almost sufficient, but you have to pass to the closure. So two orbit closures intersect if and only if every G invariant polynomial agrees on the points. So an important special case we're going to talk about a lot is the null cone, which is when one of the points is 0. So every homogeneous G-invariant polynomial vanishes on the point V if and only if the infemal norm of V over the orbit is 0. And what that means is basically 0 is in the orbit closure. And we say, if that happens, we say V is unstable. And if 0 is not in the orbit closure, we say V is semi-stable. So the thing I showed on the previous slide tells us that we can answer this question about, invariant. They have this equivalent question about invariance and orbits. And in particular, we can answer something about invariance just looking at this optimization problem on norms. So here's the optimization problem I want to solve. Just calculate the infimum of the norm of the group orbit. And we call this quantity the capacity. Any questions before I talk about applications and so on? Probably many people have seen this. Oh, hello, Michael.
I don't. Yeah.
Okay. Yeah, so the usual laundry list of applications, which I'll go through pretty quick. The permanent, Roscoe-Blieb inequalities, machine learning, isotropic position, non-commutative identity testing, quantum information, stats. Comes up a lot, and it's not always just about invariance. Sometimes it's the quantity itself that's interesting. So one example is perfect matchings. So if G is the pairs of diagonal matrices with determinant 1, and they act on matrices by multiplying on the left and right, we have this kind of old picture. The support of the matrix has a perfect matching. I guess you could say the support contains a permutation matrix if and only if this capacity looking thing is bigger than 0. And I guess Ankit told you about all this. And the third condition is if and only if there exist X and Y diagonal with this XAY being doubly stochastic. So you have the first one, which I would call an invariant theory condition. The second, by the way, because perfect permutation matrices, I want to say the monomial corresponding to them is invariant under this group G. That's why I would think of it as an invariant. And then we have a capacity condition, and then finally this third condition, which I haven't explained yet, but really it's a condition about the gradient of this function XAY. Because the gradient turns out to be the set of row and column sums. So if it's 0, well, okay, if it's proportional to the constraint, the gradient of the constraint, then you have an optimum. And there's a nice alternating minimization algorithm for this. So now let's talk about what is the picture when you don't just have a commutative group like diagonal matrices, you have a more interesting group. So the thing that we want to think of as the row and column sums becomes the Riemannian gradient of the log of the norm. The log, not so important. And don't press me to say what this means, but it is a moment map that symplectic geometers would like. For example, for conjugation, this is what the moment map would look like. If you're conjugating the matrix A, then the moment map is going to look like this normalized thing, where you have AA transpose minus A transpose A. And I guess you see that the moment map is 0 if and only if the matrix is normal, which is kind of interesting. So the analog of the theorem in the non-commutative world is, I guess, called Kempfness or Hilbert-Mumford. And it says that the capacity is 0, bigger than 0, meaning the infimum of the norm is bigger than 0 if and only if the moment map can be driven to 0. So in this picture, 2 and 2 are analogous. So the doubly stochastic scalings is analogous to the moment map being drivable to 0. And finally, the support having a perfect matching is analogous to there being some invariant that does not, homogeneous invariant that does not vanish on G, or on V, sorry. Okay. So that's some background, and here's the problems that we want to solve. So let's define a function f to be the log of the norm. And we want to optimize this. So opt is going to be the infimum. And the norm optimization question is to, given a vector v, produce an approximate minimizer, or determine that the optimum is minus infinity. And the null cone problem is just to decide if the optimum is minus infinity. Okay, so some previous things. So poly log 1 over epsilon algorithms for the norm optimization problem were known only for the left-right action. Actually, maybe I should clarify this. Really, actually, any algorithm for the left-right action, really any algorithm for norm optimization was known only for the left-right action. The other algorithms were for the moment map minimization problem, which I'll talk about later. But we also have, or there are also are some algebraic algorithms for the null cone problem, for the left-right action and the conjugation action, and probably more that I don't know about, but these algorithms actually use the invariant theory and come up with the right invariants to evaluate on, things like that. So I mentioned the scaling problem. So sometimes just rather than necessarily needing to optimize the function, we just need to send the gradient to 0. That's can be a pretty interesting problem still. So we call the scaling problem this problem where you're given the vector and some parameter bigger than 0, and you produce a group element where the moment map is at most epsilon, or conclude that the optimum is minus infinity. So the reason that you care about optimum being minus infinity here is, of course, there's no reason necessarily that the gradient would be bounded, that you could make it arbitrarily small if the optimum was not bounded. So there are poly 1 over epsilon time algorithms so far before our work for the operator scaling problem and the tensor scaling problem. And maybe what I would say now is that there are log 1 over epsilon. And this also means left-right action to stay consistent. And there's poly log 1 over epsilon time for left-right action. That's this GFL. Okay. So what we are doing is tackling both of these problems for general representations We just want to get any representation of an algebraic reductive group, but I should say it's going to be a polynomial representation. And we want to find algorithms for norm minimization and scaling in these situations that don't really rely on such specific structure as alternating minimization, things like that. And we want to figure out what drives their running time, like what makes it hard or easy to solve these problems. So we introduce two complexity parameters, the weight margin and weight norm. The weight norm is roughly just the degree of everything, and I feel like it's very sort of an obvious parameter, whereas the weight margin is more interesting, but let me kind of say what these are. So to each group action, there's a finite set omega called weights. And maybe this is not really true, but let's just imagine that G equals GLN for possibly almost the rest of this talk. Okay, so there's a finite set of weights. So instead of defining what this is, I'll just give examples. So for the left-right action, it's going to be basically a pair of standard basis vectors. So something like, you know, if n equals 3, you might have 1, 0, 0. That's one of them, and then 0, 1, 0. That's another one. Okay. Or for conjugation, we have differences of standard basis vectors. And the tensor scaling action, we have triples of these standard basis vectors. All right, so the weight margin is a bit of a mouthful, but what it is the closest that the convex hull of a subset of omega can come to the origin without containing it. Okay, so for a picture, you might have, say here's 0. Is right here. Then the weight margin in this case would be this distance right here, because this is some subset of these points omega, which does not, the convex hull does not contain 0, but it comes pretty close. And so that's the weight margin.
So sorry, okay. Can I? So you said that you'd like to interpret this as some degree. What do you mean by that?
Oh, sorry. So the this one is degree.
Oh, the weight norm is degree. Okay.
Yeah, the weight norm is like the degree.
Okay. Okay.
Yeah. So this is just the maximum L2 norm of any of the weights.
Okay.
And I guess just if you have weights, then actually just the sum of all the entries is the degree, but L2 norm is what we want to think about. Sure. All right. So,
hey Cole, can I ask?
Sure.
In your picture that you drew of, on the previous slide?
Yeah, those.
Or, sorry, I guess for these.
Yeah.
You were still talking about that. Maybe just the sets you wrote on the left-hand side, for which group actions is that? Is that GL or SL or?
Yeah, so I guess this one is, thank you. This one is GLN cross GLN. This one is, doesn't matter. Could be GL, let's just say GL or SL. And this one is GL, product of GLNs. Does that help? I could have messed it up. I think it's fine, right?
No, exactly. I was going to say, and then if you did SL, then you would project these guys right onto the.
That's right. Yes.
Traceless vectors or sum equals 0 vectors, and then actually this origin would be in the convex hull.
Yeah.
That you were talking about.
Yeah, exactly. Right, and yeah, I guess maybe that's one confusing thing is that the way I've written for example, the first and third, yeah, the origin will never be in the convex hull, because they all, the first and third sum to something that is not zero. So the origin won't be in the convex hull. But as Michael points out, for SLN, for example, the left-right action would be, let's say left-right SLN, that would be EI minus 1 over n times the all ones vector, EJ minus 1 over n times the all ones vector. So this is something that could actually, you could hope that the convex, that the origin was in the convex hull. Okay, but yeah, the way I would interpret these things is that the weight norm is like a degree, and this is almost like some kind of complexity or condition number of the problem, maybe.
If you allow me to say one more random comment,
Sure.
I mean, the fact that if you did act by GL, that then the origin is not in the convex hull, is just reflecting the fact that the null cone problem is trivial, right? Everything's a null cone for the GL
You're right.
Yeah,
action.
yeah,
So
yeah.
the interesting one is DSL from that perspective. Yeah. Then that becomes a more subtle quantity somehow to compute. Okay, we'll shut up now.
Sure. Thanks, Michael. Okay, so let's continue. Right, so the weight margin, we want it to be large, you know, if we want efficient algorithms, and this one we want it to be small. So this weight margin is what's explaining the dichotomy between what we can and can't do so far. Or at least it's one of the things explaining it. And these results are why that's true for operator, well, for let's say left-right action. For the left-right action, we have the weight margin is on the order of n to the minus 3/2. And for tensor scaling, it's actually going to be less than 2 to the minus n over 3. So polynomial versus exponential. All right. So in terms of these parameters, let's see what we get algorithmically. So the weight norm controls the complexity or the running time of first order algorithms. So when we say a first order algorithm, what it means is it should just have access to the gradient of a function. And in this case, it's the moment map. So if we have Oracle access to the moment map, we can output a point G in time with a point G with the moment map being at most epsilon in time, polynomial in n, and the optimum and 1 over epsilon. Or we can conclude that the optimum is minus infinity. I should say, you know, the way I've written it doesn't really look like a polynomial time algorithm yet, because what is opt? But one of the things that we show is that, you know, in fact, opt itself is also poly in the input size.
So how is the representation given to you?
Right. Okay. So this is a very painful thing, but I guess in some situations you have a very easy way of doing it, like for tensor scaling, operator scaling, and so on. But for other representations, what we need to do is basically, so we have a couple of things. We have to give the representation, and it's going to be given as right. So I believe that we are just looking at, so Michael, maybe you can chime in. We're just looking at, in terms of like, for this oracle result, I think we don't necessarily need this input, but for the result where we actually get the input, we're just doing it for representations of GLN and products thereof, right?
That's right. Yeah. So we worked out, I guess, these bounds for type A. Yeah.
So let's just say for just GLN. So the representation is going to be given as partition, and the algorithms are basically going to run in polynomial in the unary size of the partition. Okay. And also, you have the fact of how are you going to write down the vectors in the representation? And those are done in the Galfond-Settlin basis, which for now I'll just say is kind of a very nice basis. But yeah, maybe I think the best thing is to look at the paper for exactly what the input model is. But for I think it suffices to think about something like conjugation as a really interesting example where the basis is pretty obvious, or the basis and input is pretty obvious. Okay. Okay, and then we also have a second order algorithm for the norm minimization and the null cone problem, which given oracle access to the moment map and the Hessian of the log norm, outputs an approximate minimizer in time, polynomial in 1 over the weight margin, the weight norm, and the optimum and log 1 over epsilon. Or concludes that the optimum is minus infinity. Yeah, and so I should say that in this this input model that I mentioned, mu is also efficiently computable, and also the Hessian is efficiently computable. All right. So I want to talk a little bit about why these parameters come in to the problem. And the main nice structural way that they come in is this kind of stability result, or we call it non-commutative duality, between the moment map and the optimum or the capacity. So I think the very interesting part is that if the weight margin is small, then you know just looking at the moment map how close your vector must be to its minimum norm already. So basically, the way I would interpret this is mu gives a lower bound on opt. So like one of the problems in optimization is you can run gradient descent or something like that on your function, and all you have access to is the gradient. You don't know how far you are from the optimal point, or how far your function value is from the optimum just by looking at the gradient necessarily. But this theorem is an example of a situation where by when the gradient gets small enough that you know that you're close to the optimum. So gradient small implies close to opt. Okay. And of course, looking at this theorem, we can use it to decide if what precision we need to determine whether the vector is unstable or not. So of course, if I just look at this equation here, if the moment map is smaller than the weight margin, then I immediately know that the capacity is bigger than 0. So I just have to run my first order algorithm, for instance, until the moment map is less than the weight margin. And then I'm good to go. Right, and so you can already see that if you have this result and the first order result we had, that this implies polynomial time algorithm for null cone whenever the weight margin is polynomially bounded. So gamma bigger than 1 over poly implies poly time for null cone. Okay. And another way that these things come in particular the weight margin, is they control how far you need to look for the approximate minimizers. So we define the diameter bound of a function as, or let's say a diameter bound as the largest, or as the size of some ball, where if you look inside that ball, you'll find an epsilon approximate minimizer. So it just says how far you have to look to find an approximate minimizer, or gives an upper bound on how far you have to look. And our result is that the diameter for a specific epsilon is actually on the order of 1 over the weight margin times log 1 over epsilon. And actually this big O is hiding some things, like there's some dependence on the capacity here. But let me ignore this for now. Right. And this diameter bound turns out to be tight for tensor scaling. So in fact, the diameter bound for tensor scaling is on the order of, or I guess 2 to the minus n over 3 times log 1 over epsilon, for epsilon small enough. So really this weight margin thing isn't too loose, actually, I would say. Looking at the weight margin, it really does say something about the optimization problem, that the diameter can be this place where you have to look can be very, very large if the weight margin is too small.
2 to the plus n by 3, right?
Yeah, thank you. Yes.
One more question, Cole. So
Sure.
the weight margin comes naturally, is it, when you're trying to lower bound the capacity? Is that yeah, I mean, how did you get to this idea of looking at weight margin actually?
Yeah, so the way that the weight margin comes from the answering the question for the torus. So maybe the one way to think of the weight margin, so if you have a torus acting and it has some weights, you know, omega 1 blah blah blah, omega n say, then if you have a vector which is supported on some subset of those weights, you know, the stability of that vector, or the semi-stability, is determined by whether the 0 is in that side inside the convex hull or not. Okay, so let's call this vector, you know, has some masses on these semi-stable if and only if Okay. And the question really comes from looking at how small do you have to make the moment map in the torus case in order to know that the point is semi-stable. So it's basically like, if you have this representation, the vector could potentially be supported on any subset of the weights.
Yep.
And you want to know how precise do you have to get the moment map in order to know that the point is semi-stable. And maybe the final thing to say is that the moment map is just, in the torus case, the moment map is just the expectation of, the weight with the corresponding mass from the vector's entry. So basically, this moment map can be anything in the convex hull. So that's why you care about the distance between the convex hull and zero.
Okay. Thanks. Yeah.
Sure. All right. So as I was saying, the size of this weight margin explains the previous hard and easy cases. That why we get an optimization and null cone algorithms for the left-right action. Why we get it for conjugation. And this one is new because, well, it's okay. It's not new from the algebraic point of view, but it is new from the optimization point of view. So. And it also explains a bit some of the difficulty of obtaining the null cone algorithms for tensor scaling. And I guess this was also, people also showed that the degree is an issue here. So this also has exponential degree lower bound, meaning you have to look at very large invariants. So somehow these things seem to coincide. When you have a nasty weight margin, you might also have other parameters like the degree of the invariance you have to look at being nasty. So I guess that's Visu and harm. Okay, and what kind of new norm optimization algorithms we're getting? So as I mentioned, conjugation, but we also get polynomial time algorithms for quivers with constantly many vertices. We get it for constant rank groups, which I think the algebraic problems were already understood there, but it's also interesting to have a counterpart in optimization. And for instance, the tensor scaling problem where one of the dimensions is held fixed. And the weight margin is still not the whole story yet, because there are some examples that Visu and Philip have come up with of some interesting quivers where the weight margin is large, or sorry, the weight margin is small, but there are still efficient algorithms. So, and this relates to something called the gap, which is really, instead of looking at the set of weights, you have to look at the set of orbit closures and ask how close can the moment map come to zero of one of these orbit closures without the vector being semi-stable. So let me, maybe I'll define this really quick. So gap, this would be the minimum Okay, so what I mean is you look at all the unstable vectors and ask how small can the moment map be made for unstable vectors? Which is basically how likely are you to be tricked by looking at the moment map to decide the null cone problem. So gap seems to be a better explanation of what's going on than the weight margin, but we don't really have theoretical results using the gap yet. Okay, so let's see. All right, so before I go on, are there any questions about this stuff?
Yeah, maybe just a question for you. We still don't know if this non-commutative duality kind of estimates hold for the gap, right? That was something that we asked in our paper, but I mean we know like the constant can't be better.
Yeah,
but one could replace the weight margin. I mean, weight margin is kind of the same thing, but the torus moment map, right?
exactly.
And torus group action.
Yeah, so the question is, do we have this kind of result?
Yep.
And I think we don't
Very
know.
satisfying.
Right. Yeah. All right. So I will now go on to the algorithms. Okay, so remember what the function we're looking at is the log of the norm. And it turns out that unfortunately, a natural thing to do would be to hope for just a change of variables that makes it convex. It's great when this kind of things happen. This does happen for the torus, basically. So for torus, f of e to the x is convex, but it's not for say GLN. So this is an example of a in fact a norm being plotted here for some subspace of 2x2 matrices. You can see it's not convex. It's funny, but it is star convex, which means that if you start here and you go out, it'll be convex along those lines. In fact, it's something better happens. It's going to be what we call geodesically convex. So in general, the lines that we want to look at are of this form, e to the tx times g. So these are geodesics in some geometry. The geometry is actually on g mod k rather than g itself. So this is the maximal compact subgroup. But since we just care about optimization, we don't really need them to be geodesics. We just need some nice lines to go down. And I'll just point out that, we haven't lost anything by only going down such lines. The reason is that our function is k invariant, right? F of k, f of kg equals f of g. And maybe it's important to point out that the norm that we're using is going to be the unitarily invariant norm. This should be the k invariant norm on the vectors. So a simple situation where you can see this is the left-right action, or the tensor scaling action. In that case, it's like if U1, U2, U3 are unitary, then of course U1 tensor U2 tensor U3, V is the same as V, right? So this is why it's sort of fine to only go down geodesics that look like this. And fortunately, our function is convex along such geodesics. An example of the geometry on that you could get on Gmod K is the hyperbolic plane. This is one that comes up. So in general, they're going to be non-positively curved spaces. In fact, this is SL. Okay, I should be careful. SL2 R quotiented by SO2. So in this, and it's not the complex reductive group that we're talking about, but SL2R quotiented by SOR is the hyperbolic plane. And already all the interesting stuff shows up in the hyperbolic plane, I feel. Okay. So what is the geodesic gradient descent? You just follow the steepest geodesic at each step. And the steepest direction is going to be the direction of the moment map. That's because the moment map is the Riemannian gradient of, our function. Okay. And the algorithm starts at the identity in the group and has some step size. And it just keeps iterating to go in the geodesic direction of the moment map. Right. And so this picture on the right is kind of what this could look like in the hyperbolic plane, that you keep going along some geodesics to try to find your optimum. Okay, so how do we analyze this? We'd like to show that at some iteration, the moment map is small. And I would just, maybe before I continue, I make it clear it's not exactly a super new analysis. It's just the same analysis for the first for the Euclidean case. It just also happens to work here. The important thing is that the weight norm controls the second derivative along geodesics, which means that Taylor approximation, first order Taylor approximations become good, which tells us that sort of gradient steps make progress. So that's what I mean to say when I say that the standard analysis of gradient descent kind of carries over. And what we get is that if we take the step size to be 1 over the weight norm, and we take this many steps, basically 1 over epsilon squared, then at some point we're going to have our moment map in most epsilon. So the progress we're going to make at each step is actually around the moment map squared size. So the gradient size of the gradient squared. So that's that. Also the second order algorithm. What you do is you look at the some second order approximation for the function. But the problem is it's not going to always be a very good approximation. It's only going to be a good approximation on a small ball. So you only want to look on a ball of radius about in around G. And when I say ball, I mean in this geodesic sense. It's everywhere you can get going along one of these lines for a certain distance. And maybe I should just say the speed of a geodesic. If you have this geodesic e to the THG, its speed is going to be this norm of h. Okay. So basically, the things in a small ball sort of look like. So the R ball would look like e to the TH times G for, the norm of H being at most R. Okay, so we only trust this. That's why it's called trust region method. We only trust this quadratic approximation on a ball. And what we're going to do is just minimize the, oh, sorry, of course I lied here. Not n, but 1 over n. Because large n is not helpful for us. Right, so I'm going to minimize the quadratic approximation on this ball here. And then I'm going to just go along, go to that new point on the ball. So I have this picture, here's my function. I start here, maybe I optimize on this ball, I go here, then I optimize on this ball, go here, so on.
So this also looks like what you would do in the standard Euclidean case, right? You would take the second order approximate, the minimizer.
Right. Yeah, Newton. I guess it's like Newton's method.
Newton's method, yeah.
Yeah, but like they call it or like constrained Newton's method or something like that. Yeah. You don't want to go too far. All right.
Yeah.
Right, and again, the standard analysis kind of carries over, but what you do is the guarantees for this second order algorithm, they give you poly log 1 over epsilon algorithms as long as the diameter bound is small. So this constrained Newton's method stuff, it needs a polynomial diameter bound. So if that's the case, then you can regularize the function, which means you add some sort of nonsense to it, which doesn't affect the optimum very much, but does cause the diameter to be small. And then you can make sure that the algorithm runs efficiently. And the runtime bounds for our algorithms are then following from the diameter bound I mentioned earlier, where we showed that the diameter bound is bounded by the weight margin. Okay. Questions about this? These algorithms.
So does this extend to other convex functions also, geodesically convex functions, or
yes,
only the norm,
this should all be general, up to here.
Okay.
It's just this that is not general. I think it's just a matter of it not appearing in the literature. Basically these folks wrote this algorithm down for the left-right action. Nothing in that really needed it to be specifically the left-right action either. But yeah, it was one of these cases where nothing about it was hard to generalize, but it just didn't appear in the literature yet. Okay. So yeah, I guess we haven't had a break. Have people been taking breaks, or should I just continue?
You can just continue. People haven't been taking breaks, actually, unless you want to take a short break.
No,
water or something.
Okay. So as far as proofs goes, I wrote down a few of them, or vague ideas of a few of them. So we'll see kind of what we get through. So we might do, there are 4 things we could prove. I tried to go in the order of interesting to algebraists. But okay, let's start with the bounding of the capacity. So yeah, so remember our algorithms were like poly, maybe n 1 over gamma opt log 1 over epsilon. They had these kind of dependencies. So we need bounds on opt. So this is something important for any specific input that we want to bound how long it actually takes. So we need to bound. So we need bound on this capacity, which is the infim norm. Okay, so suppose that you have some integral vector. So of course, your vector could be rational, but you can always sort of scale it up and nothing changes. Yes, you can always scale it up and nothing changes. Another point is that really you want it to be in a complex vector space. So it should actually be a Gaussian integral vector, but that doesn't change anything in a meaningful way. So I'll just sort of assume that it's integral. And here's well, maybe let me explain what I'm trying to do. What I'm trying to do is set up a lemma, which is the main idea of how we lower bound this capacity, and it has to do with invariance. So what we're going to do is take an invariant and use it to bound the capacity. So let's let P be some invariant. And I want to go back and forth between thinking of an invariant polynomial as, well, a polynomial, but also I could think of it as just some symmetric tensor. Okay. And let's assume that we have some invariant, degree D invariant, on which the point doesn't vanish, because we only want to bound the capacity when the point is not in the null cone. So not in the null cone. Otherwise, the capacity is minus infinity or 0. Okay. So here's our lemma. If V is not in the null cone, then the capacity is at least the norm of P to the minus 1 over D. So this is the norm as like a symmetric tensor, a symmetric D tensor. Just, you know, take the sum of the squares of the entries. Okay, so let's see why this is. And I also, just to be very clear, it's very important that both the entries of this invariant and the vector is integral. So we're going to write the norm of G dot V to the 2D, which is the thing that we want to bound, raised to the D. It's equal to the norm squared of the D tensor power of the vector. Okay. And then, well, if you have the norm, oh, maybe I actually lied here. I think I should just have no squares. So the norm of a vector is at least its projection onto some direction, right? So if I project it in the P direction, the norm is going to be bigger than the size of that projection. Okay, just Cauchy-Schwarz. And then this is equal to 1 over P times P of G dot V. And the reason for that is because this translation between symmetric tensors and polynomials has the property that basically P times W tensor D, the inner product in the symmetric D tensor world is going to be equal to just the evaluation. Okay. And now, because P is invariant, that's just PV. And then finally, this is at least 1 over P because P is integral. Okay. So now all we need to do is find some invariant that vanishes on V that's integral and has small norm. Okay. So remember, we're trying to show that this capacity is at least polynomial. The log of the capacity is at least polynomial. So from the previous theorem, it's going to be enough to find an invariant with coefficients only this large. So e to the d times poly. Okay, so just because the theorem is on the previous slide, I'll just rewrite it here. So cap v is bigger than p to the minus 1 over d. Right. So we're okay with the coefficients growing exponentially in d because of this 1 over d here. And the coefficient in the exponent just needs to be at most polynomial. All right. So this is where the Cayley omega process comes in. So I'm not going to go into what the Cayley omega process is, but it's a nice algorithm to output a basis of the degree d invariance. And I think that I only know of the Cayley omega process working for basically SLN and products of it, you know. But maybe someone here knows, you know, analogs of the Cayley omega process that works for more general groups. But as far as we knew at the time of writing this, it was just for products of SLs and GLs. So we have this nice algorithm, and it turns out that you can just kind of tediously go through the steps of the Cayley omega process and check that the coefficients that get produced are going to satisfy this. And it's not really a very stringent requirement. You know, if you think about it, this is really a quite horrible number. So it's not like we're expecting for some magically small coefficients. It's more just like, you know, you go through the algorithm, you naively multiply everything that you could, you know, worst case bound to everything. It's not very hard. But the interesting thing about this is that you just need d finite. So you don't need degree bounds. So that's kind of nice. Okay. So what's next? So the next thing I want to look at is this so-called non-commutative duality bound. So I want to look at only the lower bound end of it, which is that saying that this capacity is 1 minus the moment map over this weight margin. Okay, let's only talk about torus actions for now. So hopefully Ankit's talk is in people's memory a bit, but if it isn't, I'll just remind you a little. So you can translate the vectors in this action to just probability distributions on sets of weights. And the capacity there, maybe this should be, let's say that. And the action is going to be, for now, it's just going to be CD, this torus. So the capacity is going to be the infimum over RD of this function. And in this case, the capacity actually is convex. This is a convex problem, and even its log is convex. Right. I might be missing a log here, actually. Yeah, so let's say log. Never mind. Okay. And the moment map is going to be the expectation. Right. Here's where I did lie a bit. So I want to say this needs to be normalized. Okay. In order to actually make sense as an expectation. So that's the capacity in the moment map in the torus case. And what we're trying to show again is that the capacity is bigger than or equal to 1 minus the moment map over the weight margin. Okay. So the way we prove this is using a decomposition lemma. So suppose that our probability distribution P is such that sorry, I meant to say 0 here, is that 0 is in the convex hull of its support, meaning it's stable. P is semi-stable. Okay. Then it turns out that P is going to be a convex combination of 2 other probability distributions with the following properties. So the first one is that the moment map is 0. The moment map of the first part of the convex combination is going to be 0. In particular, it means it's stable. And the other part is going to be unstable. So we kind of take it into very stable, meaning the moment map is already 0, and unstable pieces. Okay. So why is this useful for our proof? Well, on one hand, we can lower bound the capacity using this decomposition. It's just trivial because the capacity is going to be monotone under adding things, right? And remember, the capacity is like right. So if we add 2 non-negative distributions, then the capacity is going to only increase. So you can only look at this part of the sum. Okay. And then the reason for the second inequality is because the moment map is 0 here. Basically, the norm is already minimized. All right, so that's one hand. The other hand is that the moment map of P is going to be equal to S times the moment map of P double prime. And that's because, again, mu of P prime equals 0. And I'm assuming that P and P prime are, I'm assuming that P is actually already normalized. So P is a probability distribution. Okay, and then finally, we have this inequality. And this is precisely because P double prime is unstable. Mm-hmm. So I guess it's important that KV asked that question earlier, because we can interpret the weight margin as being the least moment map of an unstable vector under the torus action. All right. And now if we just put these things together just by shuffling around, right, we're just solving for S and then plugging it in up here, and we get the inequality. Okay, so I have a couple more proofs, but I think I'll skip them and go to the just talk about the open questions, since I'm kind of running out of time. yeah, so this is the proof of the decomposition lemma. It's kind of nice, but probably can come back to it if people want to see. More clever about this. Okay. So what's still open? What we've shown so far is basically that if you just make the right definitions, then all of the nice, easy optimization stuff carries over, and without too much pain, you get nice algorithms. But clearly it's not enough, because, for instance, we don't get a polynomial time algorithm for null cone for tensor scaling. So maybe we need to look at some more powerful algorithms. Maybe we should look at some kind of ellipsoid method. There actually is a non-constructive kind of version of that. So when I say non-constructive, I mean it makes the right number of queries to the gradient, but each step is kind of algorithmically challenging on its own. But even if we could make it constructive, it actually turns out to be moot, because the way that the ellipsoid algorithm works is you start out with some set that contains your optimum, and you keep cutting it down by a constant factor each time. The problem is, usually, and what kind of guarantee this gives is it says that as long as you know that this set is only exponential, you'll get a polynomial time algorithm. So for instance, diameter bound d equals exp of n or whatever is fine in Euclidean, because the volume looks like d to the n. But in fact, even in the hyperbolic plane, volume is like e to the d. So this is bad. So if your diameter bound was exponential, then your volume is e to the d. So that's a problem. So I think there really is something weird going on in curved optimization. Maybe interior point methods could solve this. I'm skeptical. But what I think what we probably have to do, and Michael and I have talked about this for sure, is that instead of, we need something very special to representation theory. So basically some other parameter that we're overlooking right now. So we need to use some kind of additional structure. I think we're not just going to be able to say, oh, it's a geodesically convex function, therefore we can optimize it. I don't think that that's going to happen. I think we need something very, very specific. And yeah, so hopefully if we do, figure out how to make optimization better, we can, solve this norm minimization problem. We can solve the null cone problem for tensor scaling and polynomial time, which actually, I mean, maybe could this problem be hard? I don't know. And finally, it would be nice to have some kind of optimization looking algorithms for orbit closure intersection. But at the moment, I think there's not even a blueprint for what that would look like, but it would be very cool. Okay. So I think I'll wrap up with that. Yeah, thank you.